Hello everyone, my name is Yifei, and today I'm very happy to be here to present our work, Balance the GC, a copying garbage collector for Golang. And to begin with, I would like to introduce myself. I would like to introduce myself. I'm a software engineer of the programming language team at ByteDance. And before I joined ByteDance, I obtained my PhD degree from UNSW Sydney, and my research topic is the static program analysis. And basically, this is a technique that analyzes the program without running them to collect some properties about the program. Because I'm really interested in the runtime techniques of the program, so after I graduation, I started working on some runtime techniques, such as the Java Virtual Machine and Go runtime. And currently, I'm working on the memory management of Go. So let's get started. Before we look into the detail of our work, I would like to give you an overview about what we have done. The main goal of our work is to optimize the performance of microservices to save the computing resources. And after we do lots of profiling of our microservices, we find a very interesting observation, and that is the generational hypothesis holds in the ByteDance microservices, which means that those services tends to generate lots of temporary objects and won't use them very quickly. And based on this observation, we developed the balanced GC, which introduce a bump allocation to allocate pointerless objects in the goroutine allocation buffer. And this allocation buffer is a large piece of memory attached to each goroutine. And then we use a copying GC to manage the memory of those buffers. And after we deploy this technique into the production environment, we can see approximate a 4% performance improvement. So this is a basic introduction of our work. And here is an outline of my talk. I will break this talk into 4 sections. First, I will introduce some backgrounds and motivate why we are focusing on object allocation. Next, I will move on the technical details about our work. And third, I will discuss some pitfalls and lessons we have learned during implementing such a moving GC. And at last, I will show some results after we deploy our work to the production environment. To the first section, and here is a product portfolio of ByteDance. ByteDance has been developing lots of the internet services, including the creation and communication, digital entertainment, and enterprise services. And behind all those businesses, we have tens of thousands of microservices are developed to support various businesses. And most of these microservices are written in Go. And ByteDance may be one of the largest Go user groups. And there are a couple of reasons why we select Go, because Go has a very flexible and expressive grammars to support efficient developing, and it has a built-in efficient and scalable concurrent mechanisms, which are very suitable to develop the internet services. And third, the Go has a GC, so that the developers does not need to care about the detail about memory management. And at ByteDance, in order to support efficient development, we have a very abundant Go microservice toolchains. For example, we have Tango, which is a downstream Go SDK with some performance enhancements and some customized features. And we also maintain a lot of software, lots of middleware. For example, Gorm, which is a tool used to interact with the database, and the KiteX, which is a RPC framework, Hertz, the HTTP framework, and GoPKG, which is a utility tool collections. And since we have so many microservices and we care about their performance, so lots of reasons motivate us to optimize the performance of those microservices. Because those services use a huge amount of computing resources, so that we want to use the optimization to make these resources used properly and efficiently. And secondly, because the daily active users of our services are continuously growing, we want to use the optimization to improve the processing capabilities of those microservices. And third, the optimization can bring a better user experience. For example, the optimization can reduce the latency of the service so that the users can use our service smoothly without lagging. So this is basically the motivation of why we are doing some optimization work. And once we decide to optimize, and the first thing we need to do is to profiling, to understand the characteristics of those services. So after we profiling lots of the service, we find some interesting observations. First, because we use the microservice architecture under which the developers tends to leverage the abilities of the existing services rather than build a new one by themselves, so that we find a massive RPCs are performed among those loosely coupled microservices. And those services tend to use JSON, protobuf, and Thrift as their communication protocol. And more importantly, we find that our service has some kind of session-based behavior. And here is a typical life cycle of such a service. First, it accepts a user request. Then some marshalling and unmarshalling actions are performed to get some actions and data from the request. And this operation will generate lots of the temporary objects. And after that, some specific business logic are performed. And at last, the results is returned to the upstream service or to the users. And then the service accepts a new request and go on. So those temporary objects, most of these temporary objects will not be used again. And so this observation inspires us to optimize this object allocation. And object allocation can be a good candidate to optimize. First, it is a very high frequent operation. And the object allocation is transparent to the developers, which means that this optimization can be easily to be integrated into the user code. And thirdly is that it is a universal optimization, which means that it can be suitable to most of the microservices. And once we decide to optimize object allocation, we need to get more insights about it. So here is a size distribution of the objects and this data is collected from a real-world microservices. And in this figure, the horizontal axis is the size of the object, and the vertical axis is the percentage. So from this figure, we can see that most of the objects are small ones. And in this example, the 88% of the objects are no larger than 128 bytes. So based on these insights and inspired by the thread local allocation buffer of the Java virtual machine, we introduced the goroutine allocation buffers, and we called it gaps. And a gap essentially is a large piece of memory attached to each goroutine. And with gap, we can use a bump allocator to allocate objects in gaps. And for simplicity, currently we only allocate no-scan objects in gaps. No-scan means that there is no pointers in those objects. And the size threshold of this allocation is 128 bytes. And this threshold is sufficient to cover most of these allocations. So let's see an example. So on the left-hand side, there is a goroutine allocation buffer, and we use 3 pointers, base, end, and top to represent it. And the pointer top marks the current using of this gap. On the right-hand side, there is a code snippet that demonstrates the bump allocation. First, we check the size of this. We check the remaining space of the gap, and if this remaining space is sufficient to allocate current object, then we use the P to memorize the top pointer, and then move the top pointer to the next position, and then return P. Then we finish allocating an object. So this is a balanced GC, and we introduce a bump allocation to allocate no-scan objects. And essentially, what we are doing here is that we introduce a new workflow of object allocation, so that we need to make sure that this new workflow is compatible with the existing ones. So in our design, each gap, which is the allocation buffer, is a large object allocated by the Go memory allocator. And this design means that all these small objects are, in the gaps, in the same gap, are marked and reclaimed as a whole. And this design will result in some memory overuse, because if there is one object alive in the gap, the whole gap is alive. So our solution here is that we use a copying GC to manage to compact the memory of those gaps. And here is an example. So there are two gaps, and the vertical dashed lines represents the boundaries among these objects. And the white objects are dead, and the black objects are alive. And because there are live objects in this buffer, so both of these gaps cannot be reclaimed. So our solution is that we move these live objects to a new piece of memory. We called it survivor gaps. Then the original two pieces of gaps can be reclaimed. So here we introduce a copying GC to manage the memory to manage the gaps that we just introduced. And to summarize, in the first section, I introduced some backgrounds about the Go in the ByteDance, and because we have so many, because all these microservices use a lot of computer resources, and we want to optimize their performance to save these resources. And after we're doing lots of profiling, we find that the frequent small object allocation can be one of the hottest program paths that are worth optimizing. And based on this observation, we introduce a very efficient bump allocation to Golang, and we use a copying GC to manage those allocation buffers. And more importantly, I think that our work shows that we can use a different style of GC to manage objects with different life cycles. For example, for those short-lived temporary objects, we can use the moving GC to manage them. And for all the other objects, we can still use the original Go GC to manage those objects. And next, I will discuss some technical details about balanced GC. First is about the object allocation. And all the objects allocated in gaps are aligned to 8 bytes. And this alignment makes our management easier. And next, we can bump allocate no-scan objects in the gaps. Because there are no explicit boundaries among the objects in the gaps, so we introduce a bitmap to mark the beginning of these objects. So let's see an example. In this example, we have a gap whose size is 64 bytes. And because all the objects are aligned to 8 bytes, which means that only at most 8 objects can be allocated in the gaps in this buffer. So we correspondingly allocate a bitmap whose size is 1 byte, and then we can allocate objects. So first, we allocate an object whose size is 16 bytes. We mark the lowest bit as the beginning of this object. Then we allocate an object whose size is 32 bytes, so that we mark the third bit as the beginning of this object, and then the remaining space of this buffer is 16 bytes. And if the remaining space is insufficient to allocate the next object, then we will mark. First, we need to do is that we mark the remaining space as a filler object. Then mark the second last bit as the beginning of this filler object. And next, we retire current gap and refill a new one so that the object allocation continues. And the main purpose of this filler object is to maintain the object boundaries. And from this example, we can see that essentially what we are doing here is that we merge multiple small object allocations into one large object allocation, so each single small object allocation is much faster. And next, let's see the performance of this bump allocation. I wrote 3 benchmarks which allocate 3 different size classes of objects. And the GC is turned off to avoid the fluctuation. And here is the results. I'm sorry for the alignment issue. So from this example, we can see that the bump allocation is much faster than the existing object allocation. Because as we mentioned earlier, all those gaps are large objects allocated by the Go memory allocator. So which means that if all the objects in the gaps are dead, then this gap can be reclaimed by the Go GC as a whole. But if there are some live objects in the gap, then this gap will be retained. and eventually the total size of gaps will exceed a threshold, and then we need to do a balanced GC evacuation to reclaim those memory. And the question here is that when do we check the total size of gaps? One possible solution is that we check when we refill the gap, because at this time we actually allocate a piece of memory. But we don't think this is a good design, because we introduce some redundant checkings, and the gap refilling can be a very high frequent operations. So our solution here is that we estimate the size of gaps that could be allocated in the next GC cycle. And let's see an example. So at the end of current GC cycle, we have known the total size of the live heap objects. And a part of these objects are gaps. And the Go GC and the Go memory management will tell us the heap goal of next GC. And based on this data, we can estimate the gaps that are allocated in the next GC based on the history allocation. And if the estimated gaps plus the live gaps does not exceed the threshold, then the evacuation is not a trigger, because we think that the Go GC can effectively reclaim those gaps. But if the total size exceeds the threshold, then the gap evacuation, the balanced GC evacuation is triggered in the next GC cycle. So here is the triggering strategy of balanced GC evacuation. So next, so if we decide to do evacuation in the next GC cycle, the first thing we need to do is that we need to do some extra things during GC marking. The balanced GC marking is performed together with the common Go GC concurrent marking. And the main purpose of the balanced GC marking is to collect the location of live gap pointers and put all those pointers into a pointer queue. And let's see an example here. So in this example, we have object O, and O.f points to a gap object A. And the GC marking marks alive the object O, and the balanced GC marking will collect the location of live gap pointers. And in this example, it is the address of O.f, and then put this pointer into a pointer queue. And at the same time, the balanced GC computes the total size of live gap objects, which will be used in the later balanced GC evacuation. So the question here is, how can we determine the size of gap objects? As we mentioned earlier, there are no explicit boundaries among the gap objects, and Go allows the interior pointers, which means that given a pointer points to a gap object, and we cannot tell the beginning and the end of this object. Because we use the bitmap to mark the beginning of this object, so that we can leverage this bitmap to compute the size of these objects. So let's see an example. In this example, we have a pointer P points to a gap object. And since the objects are aligned to 8 bytes, first we need to do here is to find the 8 byte that covers the pointer P. And then we find the corresponding bit in the bitmap of this 8 byte. And next, we count the consecutive zeros before and after this bitmap. And in this example, we find that there are 4 bits corresponds to this object. Because the objects are aligned to 8 bytes, so we can say that this gap object, the size of this gap object is 32 bytes. Okay, let's go back to the GC marking. And after the GC marking terminates, and all the location of live gap pointers are discovered here, and these pointers are stored in a pointer queue, and the total size of the live gap objects is also computed. And next, we will go to the balanced GC evacuation. First, the evacuation is performed during a mark termination phase, which is a stopped word GC phase. And second, we allocate a survivor gap according to the total size of live gap objects, which is computed during we are doing balanced GC marking. And next, we will process the pointer queues until it is empty. And let's see an example. And in this example, we have 2 objects, both x.f and y.f, points to a object A. And on the left-hand side, we have a survivor gap, which is the destination of evacuation. And on the left-hand side, we have a pointer queue, which is waiting for processing. So first, we pop up the first pointer, which is the address of y.f. And we find that it's this pointer. This pointer points to a gap object. And then we copy this gap object to the survivor gap, and then the old copy of the A is forwarded to its new copy. And at last, we use the address of the new copy to update the object Y so that we finish processing the first pointer. And next, we're going to process the second pointer, which is the address of x.f. And we also find that this pointer points to a gap object, but this object has been forwarded, which means that they have already been copied to the survivor space. So what we are doing here is that we use the forward pointer to update the x, so that the x now points to the new copy of the object A. So basically, what we are doing here is we implemented a very typical moving GC by using the forward pointers. And after all the pointers in the pointer queue are processed, which means that all the live gap objects are moved to the survivor gaps, and their pointers has been updated to point to its new copies. And to summarize, in this section, I introduced some technical details about the balanced GC, and balanced GC allows use a bump allocation to allocate the no-scan objects in the per routine allocation buffers. And now those buffers can be managed by two GCs. First is the Go GC, which will reclaim the gap as a whole, and second is a balanced GC, which reclaims the free memory within these gaps. And conceptually, I think that our work introduced a different style of memory management to Go, which is a copying GC. And in the next section, I will discuss some lessons and pitfalls that we have encountered during we implementing such moving GC. So, because we all know that the Go GC is the Mark Swift GC, which concurrent Mark Swift GC, which does not move objects. And some code has take this as an assumption, so that we need to make sure that the copying GC introduced by the balanced GC is compatible with all those existing code. And in this talk, I will use the Go map as an example. And we found two incompatible issues here, and I call the first issue the changing object hashcode, and the second one is called hidden overflow pointers. And due to the time limitation, I will mainly introduce the first issues here. And before we look into these issues, let's get some backgrounds about the Go map. So a Go map has one map header, which is called HMap, and several map buckets, which is called BMap. And map buckets stores the key value pairs. Usually, there are 8 key value pairs in one map bucket. And on the right-hand side, there is a memory layout of a BMap. To begin with, there is 8 top hash, which is used to fast locate keys in this BMap. And then there are 8 keys followed by 8 values, and at the end there is an overflow pointer points to other other BMaps in this map. And essentially the Go map is a hash map, which means that we use the hash code of the object to quickly locate keys in the map. And developers can design their own algorithm to compute the hash code of the object. But no matter how you design your algorithm, the hash code of the object should be consistent, which means that the hash code of the same object should be the same integer, no matter when it is computed during the program execution. And the strategy here is that we compute the hash code on demand. And for the language like Java, we compute the hash code only once and store this hash code into the object header. But we do not have the object header in Go, so that we have to compute the hash code of the object every time we use it. And the algorithms that we used to compute hash code is the AES encoding of the object memory. And this design will bring some challenges to all kinds of the moving GCs. Let's see an example here. If we have a map whose key contains a pointer points to a gap object, and then we move this gap object from P to Q, and we have to update the content of this object to point to its new copies, then the hash code is changed, and which is a very severe issue because we may incorrectly says that this key does not present in this map, and this will change the behavior of the program. So our solution here is that we introduce a object pinning mechanisms. First, we add a special mark bit in the B map, and during the balanced GC marking, all the gap objects pointed by the map buckets are pinned and are marked are not copied during the balanced GC evacuation. Because the object pointed by key is not moved, so the content of this object is not changed, then the hash code of this object is not changed. So here we introduce a object pinning to mark some objects that are unsafe to be copied during the balanced GC evacuation. And to summarize, in this section, I discussed some incompatible issues we have encountered during we developing balanced GC. Because the Go GC does not move objects, and some code may use this as an assumption, so that we need to make sure that the balanced GC is compatible with all this existing code. And we introduce the pinning mechanism to mark those objects that are unsafe to be copied. And we also have some other incompatible issues, such as SIGO. And after we testing after we running test cases and deploy our work to the environment, to the best of our knowledge, we do not find other incompatible issues currently. And at last, I will show, because we have already developed the balanced GC and handle those incompatible issues here. So now we are going to deploy this work to the production environment. So we have a standalone runtime option to turn balanced GC on and off, and we enable balanced GC in plenty of the ByteDance microservices, and we compare the performance. Before we enable and after we enable balanced GC, and this comparison is performed between clusters rather than single pods, because this comparison can remove those noises introduced by the cloud-based infrastructures, and we can get more convincing results from this comparison. So here is basic results. Roughly, we can see approximate 4% performance improvement on average in the CPU rate. And for some good cases, for example, if more than 50% or 50% of the objects can be allocated in gaps, we can see a very good results, and that is a 10% performance improvement. And we know that the current implementation of balanced GC is just a beginning of optimizing object allocation, and we have lots of future work that we can do. For example, we want to introduce the parallel evacuation to cut down the evacuation time, because currently the evacuation is performed at the mark termination stage, which is the stop the word GC phase. And by introducing the parallel evacuation, we can remove the spikes of the GC pause time. And secondly, we want to use the bump allocator to allocate more objects, for example, to allocate scan objects. And thirdly, we are thinking about introduce the concurrent evacuation so that we don't need to maintain these pointer queues during the balanced GC marking. And to summarize, in this talk, I introduced our experiences in optimizing the performance of Go microservices. And after we profiling those microservices, we find that the high-frequent temporary object allocation can be a good candidate to optimize. And according to this observation, we introduce balanced GC, which bump allocates small no-scan objects and use copying GC to manage those memories. And after we develop the balanced GC and solve the incompatible issues here, and we deploy this into the production environment, we can find the performance improvement of the microservices. And more importantly, I think that our work demonstrates that it is feasible that we can use a different style of memory management to further boost the performance of the Go programs. And at last, we are happy to contribute our solutions and our experiences to the community to make the moving GC as an option of the Go GC. And thanks for your time. This is my talk.